Welcome, everybody. My name is Daniel Carrillo, and today I'll be presenting my research project called Geometric Vanishes. So for my presentation, I would like to start with an illusion. So on this slide, we have a white rectangle, and let's assume this white rectangle is a piece of paper, and it has 13 lines of equal length on it. So just to make sure, let's go ahead and count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so for this solution, I'll go ahead and cut this piece of paper diagonally and make one of these lines vanish. All right, so now that I cut the piece of paper, I'm gonna go slide them inward, those pieces, and we now have 12 black lines. Just to make sure, let's go ahead and count the lines. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how is this possible? Well, I'm gonna go ahead and explain how this happens. All right, so if we look back on the image where I made the cut, you can see that when I made the cut, the far left line pointed by the blue arrow is not being affected, and as well as the far right line. It doesn't get affected by the cut, but the 11 lines in the between those lines, pointed up by the black arrow, those lines actually get affected. So those 11 lines get cut into 12 line segments, and whenever the sliding effect happens, the segments get distributed evenly into 12 equal lines. And because of that, we also get besides having 12 lines, these 12 lines actually increase a tiny bit compared to the original 13 lines. And the total increase of the 12 lines is equal to one of the original 13 black lines. And so if you think about it, technically all the 13 lines are still in the original 12. So this principle is actually called the principle of concealed distribution. This principle lets the objects be rearranged into new similar objects, but still keep the integrity of the original. All right, so what if we want to know how much did each line increase by? So let's go ahead, we can use a couple of mathematics in order to find out this. So we're gonna let y equal the length of the original lines, and let x equal the length of the new lines. So we can set up the equation 12x equals 13y. The reason why 12x, because we got 12 of the new lines, and the reason 13y is because we got 13 of the original lines. So we're gonna solve for x on this problem. So we're gonna first divide 12 on both sides, and we got x equals 13 over 12y. And notice that 13 over 12 is an improper fraction, and we can turn that into a mixed fraction. Now we got x equals 1 and 1/12y. And now notice that we can convert that fraction 1/12 into a decimal. So now we got x equals 1.083, where the 3 is repeated. And based on what we did, we can say that the length of the new lines increased about 8.3% compared to the original lines. Right, so next we got a puzzle called Get Off the Earth. And this is a famous puzzle created by Sam Lloyd, who was a famous puzzle maker. And this puzzle is really similar to the one of the 13 lines, where we're basically replacing the 13 lines for 13 men, and we're also replacing the piece of paper with a globe. And in order to appreciate this more, I'm gonna go ahead and exit out in order to appreciate more this illusion, I'm gonna go ahead and exit out my presentation and click the link that is below the title of Get Up the Earth. So if you guys can give me a second while I do that. All right. So we got over here the Get Off the Earth puzzle. And just to make sure how many men, so we got men around the globe, right? So let's go ahead and count them to see how many there are, starting from the northeast. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 men. All right, so now observe what happens when I rotate the globe counterclockwise. All right, so as you guys saw, like some of the pieces of the man sort of moved. And see, now let's go ahead and count the men starting from the northeast. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so one of the men vanished. Where did he go? All right, so now I'm gonna go ahead and go back to my presentation. All right. All right, so as I mentioned before, the get off the earth puzzle is similar to the one of the 13 lines. This means that the reason why one of the men vanished, it was because of the principle of concealed distribution. So if we go to the next slide, we can separate both pieces and observe more closely how the way that sort of this was placed and cut. So starting from the top image, the top piece, where outside of the outline of the earth, of the globe, we can see that starting from the far left, we can see that it's an almost complete man. And if we go around it clockwise, around the outline, we can see that the amount of men start to decrease gradually. And similarly with inside the globe, you can see there's a small portion of a man, small portion of a man. And as we go counterclockwise around the globe, sorry, as we go clockwise around the globe, we can see that the men start to gradually increase. So I thought it was a really good observation by separating both pieces of Get Off the Earth. So moving on, we get our next puzzle, which is a very interesting one. And this puzzle was created by Martin Gardner, who's also a puzzle maker. And I'm gonna go ahead and show you a clip of me performing this puzzle. All right, so as you saw that by rearranging the pieces of the original puzzle and changing it to and moving them into a new similar figure compared like the original one, we can see that we got a missing piece in the middle. So why is there a missing square in the middle? Because as you saw in the clip, I did not remove any of the pieces. So why is that? And this type of puzzle is actually called the geometric vanish. Right, so over here we got a second example of a geometric vanish that is similar to the previous one, but in this case we got an isosceles triangle-like figure. So take a look at this clip of So just like the previous example, by moving the pieces into a similar figure like the original one, we get a missing piece of area. Why is that? All right, so this is so here we got a third example of the geometric vanish, and this type of geometric vanish puzzle is famously known as the missing square puzzle, and also known as Curry's paradox. And this was invented by Paul Curry in 1953. And little did Paul know that he was going to create one of the most iconic geometric vanishes of all time. And back when he invented it, it was really considered as magic because nobody really knew the reasoning behind it. In this case, the mathematics behind it. So I'm gonna go ahead and play a video of me performing Curry's paradox. Yeah, so as you can see, similarly like the previous two puzzles, we can see that just by moving around the pieces into a new figure that looks like the original one, we get a missing piece of area. And I'm gonna go ahead and explain in this next slides how is this possible. But first, I would like to answer this question. So, what conditions must exist in a geometric vanish for the amount of disappearing area to be a whole number? Okay, so I'm gonna go ahead and place both states of Curry's paradox, the original and the new figure. All right, so as you can see, they're placed in the grid, and the pieces are also color coded, so it's easier to distinguish. So why don't we go ahead and find out the height of both figures? Let's go ahead and start with the first one. So we got 1, 2, 3, 4, 5 units of height for the top figure. What about the bottom? We got 1, 2, 3, 4, 5. Interesting. We got the same type of height on both of them. Now, what about the base? Let's go ahead and start with the first one. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. All right, let's go find out how long is the base in the bottom figure. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So as you can notice, although we rearranged the pieces in a different manner to get a similar piece, sorry, we rearranged the pieces to get a similar figure like the original one, we actually kept the height and base measurements. And if you look closely on the bottom figure, we can see the missing square is actually a 1 by 1 unit square. And the area of a 1 by 1 unit square is 1. All right, so now that we know that both figures have the same height and base, let's go ahead and overlap them or superimpose them. All right, so here we got the first piece over here, the first figure, that's a little bit transparent. And the reason why it's transparent is so whenever the superimposing happens, it's easier to see what happens. So here, now we got them superimposed. So if we look closely on the long side of the figures, if we get the difference of the area from both figures, we get a very thin figure, very thin shape. And this shape is actually a parallelogram. And the reason that we know it's a parallelogram is that it has the opposite sides that are both equal and parallel to each other. Here, if you look even closer, you can see that the sides of the parallelogram are actually composed by the hypotenuse lengths of both the red and the blue piece from both states. And the reason, you might be asking, how is this possible? By overlapping them, we get this very thin shape. Well, the reason why is that the original figure is actually concave. That means that the original is actually rounded inward or hollow from the long side. And the new state is actually convex, which means it's rounded outward or curved. All right, now our new goal is going to be to find out what is the area of this thin parallelogram. So before I do that, I would like to introduce you to some higher concepts of mathematics. So we're gonna go ahead and start with vectors. All right, so what is a vector? So quantities that have only a magnitude are called scalars. So a scalar is basically a quantity represented by a whole number to sort of represent a type of measurement. So for example, a scalar can be represented as a unit of length, could be represented as unit of mass, and etc. And if you gave a scalar a magnitude and direction, you create a vector. And vectors can be plotted at any point in space as long as it maintains its original magnitude and direction. So in case you don't know what a magnitude is, it's a fancy word for size length. And therefore, any two vectors are any point in space that have, sorry, let's start. Therefore, any two vectors at any point in space that have the same magnitude and direction are equal. And this type of property is called vector equality. So if you look on the top images over here, starting from the far left, we are able to represent vectors in different forms. So we can represent it as a point or ordered pair. We can represent it as a matrix in matrix form. We can represent it as a graph or as an equation. All right, so let's go ahead and plot the. So we know the sides of the parallelogram actually have to be a whole number, right? So let's go ahead and plot the sides of the parallelogram into vectors, and starting at the point 0, 0. So as you can see over here, I color coded it so the blue vectors actually have the magnitude of the blue vectors is equal to a hypotenuse length of the blue triangles, and the red vectors magnitude has the hypotenuse length of the red triangles. And also name the points, label the points in order so we can refer to this parallelogram as ABCD. So we're gonna go ahead and show you that these two vectors are equal. So like the blue vectors are equal to each other and the red vectors are equal to each other. So let's go ahead and start with the blue ones. We can do this by doing the rise over run method. So over here, you can see the arrow. If we go to the right side, starting from 0, 0, if we go 5 units to the right and go 2 units up, we end up at point D. But if we connect the points A and D, that gives us the vector AD, which is the blue vector. And over here we do the same thing with vector BC. We try to measure it and based on rise over run, we can see that we need 5 units. You need to go 5 units to the right and 2 units up. And you connect those 2 points to starting and ending points, we get vector BC. And therefore, we can say that vectors AD and BC are equal. So in a similar way, we can show that with the red vectors. So as you saw, so in order to get vector AD, we need to go 5 units. Sorry, we need to go 8 units to the right and 3 units up, and connect the terminal points of A and D, and we get vector AB. And then we do the same thing for the top red vector. We need to go 8 units to the right and 3 units up, and we can see it's the same thing as vectors AB. So therefore, we can say that DC and AB are both equal. All right, so for simplicity, let's go ahead and for simplicity, let's go ahead and call the blue vectors as vector V with the component of 5, 2, and let's call the red vectors W with a component as 8, 3. And the reason they both have the same because we previously showed that the blue vectors are equal to each other and the red vectors are equal to each other. All right, so now let's move on to matrices. What is a matrix and how do you calculate the determinants of a matrix? Okay, so on the left side, we got a general matrix A, which is a 2 by 2 matrix. And a matrix is a rectangular array of numbers, symbols, or expressions, arranged in rows or columns. And if you look closer over here, where the lowercase a is with the subscripts, those terms are actually called entries. Okay, so if we take a look on the right side, we can see we got an example of how to find the determinant of a 2 by 2 matrix. So in this example, the first thing that we're gonna do is basically cross multiply the entries. So in this case, we're gonna cross multiply 1 and 4, and we're gonna also subtract the products of this cross multiplication. So we're gonna first multiply 1 times 4 and subtract 2 times 3. And we're gonna first do the multiplication. And if we do that correctly, we should get 4 minus 6. And once we subtract that, we get -2 as our determinant for this matrix. So based on what we did, the determinant of a matrix doesn't have to be necessarily a positive number. It could also be a negative. Okay, so now that we gathered all this information, we're now able to calculate the area of the parallelogram ABCD. So as you can see, sorry. So as you can see in the top, I went and restated the vectors V and W, which can be seen on the bottom. So, and now we're gonna go ahead and recall that we were able to represent. Sorry, Mr. R. So recall that we're able to represent vectors into matrix form. So we're gonna go ahead and do that for vectors V and W. So once we got them in matrix form, we're gonna go ahead and find the determinants of these two vectors. So one thing that I did for this problem, I went and go ahead and put absolute value bars, and I'll go ahead and explain why later. So we're gonna first do the cross multiplication, right, to find the determinant. So we got 5 times 3, and we subtract that from 8 times 2. We do the multiplication first, we should get 15 minus 16. And then we do the subtraction, we should get -1. But remember that we got those absolute value bars. So the reason that I put those absolute value bars is because we cannot have negative area. So what it does, in a way, if we get the absolute value of something, it just turns it into a positive number. So the absolute value of -1 is actually 1. So based on what we did, the parallelogram has ABCD has the area of 1. And you know what else has the area of 1? The missing square from Curry's paradox. So therefore we can conclude that the parallelogram has the same area as the missing square. So as you can see over here in the bottom, on the bottom part of the slide, this is actually not an image, it's actually a video clip. And over here, what I'm gonna do is just play this video clip where we can see that sorry, they're gonna say that again. All right, so now we're gonna go ahead and take a look at this video clip where you can see the space of the parallelograms is the same space as the missing square. All right. All right, and the reason that this is actually possible is because we're using the property of concealed distribution. All right, so now going back to the question that I was trying to answer, what conditions must exist in a geometric vanish for the amount of disappearing area to be a whole number? So I came up with these statements that I came up with these statements that will satisfy this question. So by superimposing both states of the geometric vanish figure, the difference of the area of both states is equal to 1 or more parallelograms. We can represent the sides of the parallelogram as vectors that can be plotted in the graph at a fixed point. So for example, 0, 0, which is the origin point. The area of the parallelogram is equal to the total amount of disappearing area from the geometric vanish. And if the vectors define the sides of the parallelogram are defined with integer components, then since the set of integers is closed under addition, subtraction, and multiplication, it follows that the amount of disappearing area is equal to the whole number. All right, so this concludes my presentation. And over here on the next slides are my references that I used this presentation. So thank you for your time and attention. Let us say that one more time. So thank you for your time and attention.